Hi everyone, this is Carlos with the Exoplanet Modeling and Analysis Center, here with another tutorial. Today we are going to be looking at p-winds, an open source Python code to model planetary outflows and upper atmospheres. So p-winds provides us with an awesome Jupyter Notebook tutorial. So we're just going to go ahead and click this button and that will take us here. So in this example, we are going to learn the basics of using p-winds to model the upper atmosphere of some planet. And there is a couple caveats. This planet needs to have a hydrogen-helium dominated atmosphere, and it cannot have a lower atmosphere above 10 to the negative 7 bars. So the first thing we're going to do is we're going to load in all of these modules. Easy as that. Next thing, we are going to start by setting some planetary and stellar parameters to model the upper atmosphere of HD 209458b. And if you don't know what planet that is, it is this little guy right here, or actually this big guy right here. This is an artist's interpretation of this hot Jupiter that is something around 7 million kilometers away from its star. And for reference, the Parker Solar Probe just passed the sun's atmosphere at about 11 million kilometers away. So we are going to be using some of Parker's science in this notebook. A couple things we need to assume. We need to assume that it has an isothermal upper atmosphere with temperature of about 91,000 Kelvin and a total mass rate loss of 2 times 10 grams per second. We also need to assume that the atmosphere is mostly made up of hydrogen and helium, only made up of hydrogen and helium. Hydrogen has a number fraction of 0.9. Okay, so in this cell, we are defining some of our planetary and stellar parameters. So we're just going to go ahead and enter that, and all of these will be used later on. Now that we have our parameters set, the next thing we can do is calculate the steady state distribution of hydrogen in the atmosphere, neutral or ionized. Before we can do that, we need to have some sort of spectrum. And so what we're going to do is we are going to use the sun spectrum for these calculations, just to keep things simple. And also, HD 209458, the star, is a sun-like star, so this is okay to do. Now that we have our spectrum, the next thing we can do is calculate the distribution of ionized and neutral hydrogen in the atmosphere, and this involves calculating the differential equation 13, cited here in this paper. So that equation is, this guy right here. So this equation is essentially, what we are essentially going to do is plot the distribution of ionized and neutral hydrogen as a function of radius. So in order to do that, we go down here. We're going to use this hydrogen dot ion fraction, which essentially is that equation, and we're going to give it all of these input parameters that we defined up above. We're going to run that, and then down here, we're actually going to see what that looks like. So in this distribution, we have the number fraction, and the blue line is neutral hydrogen, and the orange line is ion hydrogen as a function of radius of the planet. Now that we have that, our next step is to calculate the structure of the planetary atmosphere in terms of density and velocity, because remember, we are trying to characterize the upper atmosphere of this planet. In order to do that, we are going to use this Parker.structure module, and this will calculate that for us. So here, what we are doing is we are setting the speed of sound in kilometers per second. We are giving it a radius where the sonic point will be, and so on and so forth. All we're doing here is simply plotting our plot. So let's go ahead and run that. And this is our distribution. So in blue is our velocity, and in orange is our density. And then the dots are the sonic points. Awesome. Now what we're going to do is we're going to calculate the population of helium in a singlet, triplet, and ionized states using this helium.population_fraction. And so what this will do is we will feed it some parameters, some variables, and it will do the calculation for us. Now that we have that, down here, we're actually going to plot what that looks like. So let's go ahead and see it. And here it is. So this is number density as a function of radius. And here we have helium in blue as the singlets, in orange the triplets, and in green ionized helium. Awesome. Next thing. So now that we have the volumetric densities of the helium triplet, we can calculate the spectroscopic transit signal using simplified ray tracing and radiative transfer. And before we do that, we are going to find where our planet is transiting the star, and we can define that ourselves. So here we're going to give it our planetary radius, our array of altitudes, and so on and so forth. We're going to assume that the phase is between negative 0.5 and 0.5, so that the planet looks like it's transiting right in the middle of the star, like so. This will make our calculations easier. So now that we have that, the next thing we can do is calculate the radiative transfer to estimate the spectroscopic signal in the helium triplet. So the helium triplet has properties of transitions that we need to know, and we can use the microphysics module to return these properties. And then we're going to use the transit.radiative transfer function to actually get the answer that we're looking for. So down here, as you can see, the W's correspond to wavelengths, and the F's correspond to oscillator strength. And so using microphysics, we are going to input our helium triplet parameters, we're going to input our helium triplet properties. Down here, we will give the helium atomic mass in kilograms and wavelength in microns. Then we will do our radiative transfer calculation down here. And so let's go ahead and run this and see what our plot looks like. And this is it. This is the transit signal. Simple as that. Now, if you don't have a spectrum handy, you can still use p-winds to characterize your upper atmosphere. Simply assume some monochromatic fluxes at specific wavelengths, like we did here. Input those variables. So let's plot this. Now this is similar to what we did up above. Here we have the hydrogen number fraction and radius of a planet. In orange is ionic hydrogen, and in blue is neutral hydrogen. We can also calculate the helium population using monochromatic fluxes as well, same as we did up above. And here they are. Easy as that. So that is p-winds. I hope you guys enjoyed that. It is a really useful tool, and it's really cool that we have touched the sun, and now we have this to characterize planets that are also touching their sun. Thank you. Peace.